Okay, welcome back. We have been calculating the limits of some rational functions, and after trying direct substitution first, we factorised either the numerator or the denominator or both of these rational functions to calculate a limit. Now, it doesn't matter in this case if the function is defined at the limit we are calculating for. We're only looking at the values of the function as x tends toward a. Okay, so we're not looking at what it is when it equals a. So the formal way that we write this, and we have been doing so, is the limit of a function represented here by fx as x approaches a or tends toward a is equal or is L. So just to remind you, when we do calculate the limit of a function, we don't consider x equal to a. Now, for this reason, it doesn't matter if the function is defined at a or not. Okay? So we are looking at the behaviour of the function near a. When we're able to evaluate a limit by direct substitution, like we have in the past, where we haven't had to factorise, we say the function is continuous at a. So, an example of this is, let's draw it on the Cartesian plane. So let's say we have function fx. Here's our function here. I've drawn it on the Cartesian plane, which is the set of x and y axes. Obviously it goes in the negative direction both ways as well. But let's just look at it here. Now, let's put the value a here, and we are looking at the behaviour of the function as it tends towards a, not at a. And what we see is we get a value L, which it approaches from either side. As it tends towards a, so too does the function tend towards L. And this is what a limit is, essentially. So it's all a bit of an abstract kind of concept, but that's what it is in graphical form. Okay? Now, I just want us to have a quick look at let's evaluate another limit of a rational function. So let's calculate the limit as x tends to 1 of x squared take 1 all over x take 1. Now, like we've done in the past when we evaluate rational functions, first we do direct substitution. 1 squared take 1 equals 0 over 1 take 1 is 0. So that's given us the indeterminate form. Now, we do need to stipulate that we do not want to evaluate this at x equal to 1. So x cannot equal 1. Sorry, you can't see that. X would not be equal to 1. So in that way, we are able to factorise the numerator and the numerator. So let's go ahead and do that. Now, in the numerator, you have the difference of squares. The difference of two squares. because you have x squared take 1. So when we factorise this, we get x take 1, x plus 1, because 1 squared is 1. And that's already over. So let's rewrite this limit, sorry. Limit as x tends to 1 of x take 1, x plus 1 over x take 1. Alright, what's the common factor here that we can eliminate? Well, we have the x take 1, both in the numerator and the denominator. The reason we can eliminate that is because we do not want to know x not equal to 1, which means x take 1 must not equal 0. So that's why we can eliminate these factors. So we end up with evaluating the limit as x approaches 1 or tends towards 1 of x squared take 1 over x take 1 equals, and here we do a direct substitution, 1 plus 1 is 2. That's your answer.